Okay, so today we have the second day of the summer intern presentations, and we have presentations from two projects. First up are Beth, Patrick, and Luke. They were mentored by Shane, and they're going to tell us about demonstrating perfect quantum state transfer through a chaotic spin chain.
Our project was to try and demonstrate perfect quantum state transfer through a chaotic spin chain. So during this presentation, myself, Patrick, and Luke will sort of explain what is perfect state transfer, why is it relevant, what impact does a chaotic Hamiltonian have on it, and then we're going to try and move towards showing that it is possible to do it through a chaotic spin chain by looking at a fairly recent discovery called quantum many-body stars. So why exactly are we interested in this? In previous experiments that have looked at perfect quantum state transfer, they have been able to achieve it, but they've always used Hamiltonians which are non-chaotic or integrable. So this kind of poses the question, does having a chaotic Hamiltonian kind of break this perfect state transfer, or is it still possible? So if we were able to show this, it means that there would be a lot more systems that we could utilize this, and it's very useful with things like with quantum computation, because realistically in a lot of real physical systems we're not going to have an integrable system, we're going to have chaos. So where does it come into quantum computation? Quantum computation is the use of the quantum states of subatomic particles to store information, and it has many applications such as artificial intelligence, cybersecurity, and many more. And basically if we are able to use perfect state transfer within quantum computation, it would allow you to basically take data from one part of the quantum computer and transfer it about, which is a key component of quantum computation, and we're having a bit of difficulty with it at the moment. So quantum computers use qubits or quantum digits. So while with a classical computer you have a classical bit, it can be in a state of either 0 or 1, and it's used to store data. However, the qubit or quantum bit is basically a quantum version that allows you to be in a superposition of both the 0 and the 1 state at the same time. And for example, if you wanted to increase to any value of d, it works the exact same way. So a qubit would be a 3-level system, and that allows you to be in state 0, 1, or 2. But returning to a qubit example, as soon as you measure a qubit, it will go into 0 or 1, and this is called a collapse. And when this happens, it's irreversible, you can't go back. That's why the ability to transfer data accurately is so vital with quantum computation. So what exactly is this perfect state transfer that we're talking about? Perfect quantum state transfer is a transference of the state from one qubit to another within a system or a chain after the system is allowed to evolve over time through a Hamiltonian. So here we have a one-dimensional chain of qubits, and the initial state at t equals 0 for the first qubit, its state is alpha naught plus beta 1. Now we allow this system to evolve over time, and at time equals t, we see that the final qubit is now in the state alpha naught plus beta 1. So this has been transferred from the first qubit. And basically we want to try and achieve this over the chaotic Hamiltonian. So first of all, we set up our system using the XX Hamiltonian. Now this is an integrable Hamiltonian, but we wanted to just see the perfect state transfer is possible and we can achieve it. So here, an important note is that the Hamiltonian and the sum over Zn is actually, they commute. So this means that we're able to split the Hilbert space that we're working in up into a series of subspaces. And these subspaces are characterized by the number of qubits that are in one state, and this is known as the number of excitations. Now, for our purposes, we're going to be focusing on the single excitation state, but this will be talked about a little bit later in the presentation. So here we have a lot going on. So the x, the y, and the z are the sigma x, sigma y, and sigma z Pauli matrices. And for our purposes, they are a 2 to the n by 2 to the n matrix operator, which basically acts on the nth qubit. So the term at the end has a Bn coefficient. Now for our purposes, we set it to 0. This is a magnetic field strength. And then we want to look at this other coefficient, Jn. So this is a coupling factor. And in order for us to achieve perfect state transfer, there are a couple of different symmetry conditions that we have to meet. So we have set up the Hamiltonian as a tri-diagonal matrix, and this is a form shown on the left. Basically, the only non-zero elements can be on the main diagonal. And when we set up our Hamiltonian in this way, we can set up a necessary and sufficient condition for Jn that is shown here. It's a half the square root of n times n minus n. And this basically takes into account all the symmetry conditions we need to meet, and it's sorted out. And when we set up the Hamiltonian in this way, and we let the system evolve, it actually shows the perfect state transfer is achieved. Now, we can see this by using the transfer fidelity operator. So the transfer fidelity operator is shown here, and its expectation value, when it equals 1, shows the perfect state transfer has been obtained. And we can see from this graph that it does hit 1, so we have achieved it. But obviously the XX Hamiltonian is an integral system, so there's no chaos yet. And it's a very particular form. So we looked at what happens when you actually deviate away from this form a bit. So we've added in this small perturbation, and it is a random 2-qubit Hermitian operator. Now, whenever we add this in and we let the exact same system evolve over time, we see the perfect state transfer doesn't happen. It only goes as far as 0.5, so we're nowhere near the 1 that we need. So here we have started adding chaos, and there is no perfect state transfer. This shows that the XX Hamiltonian is very fragile, and I'll let Patrick explain why exactly this is lost.
All right, so Beth has just shown that perfect state transfer fails once we deviate from the XX Hamiltonian. Adding a generic local perturbative term makes the Hamiltonian look random. From this observation, we introduce our working definition of quantum many-body chaos, which is that a chaotic Hamiltonian is one that appears random. Now, the Hamiltonian isn't truly random because the local interactions on neighboring qubits gives the Hamiltonian structure. It just sort of looks like it is random. Now, this definition may seem very hand-wavy, but we can use it because there is no universally accepted definition of quantum many-body chaos. There are, however, diagnostics we can use to illustrate it, such as the energy level spacing statistics and the average gap ratio, which are based on the eigenvalues of the Hamiltonian, and the von Neumann entropy, which are based on the eigenstates of the Hamiltonian. Starting with the energy level spacing statistics. Energy level spacing statistics analyze the distribution of spacings between consecutive eigenvalues of a system. They can determine whether or not a system is integrable with regular predictable behavior or chaotic with more random complex behavior. The Wigner-Dyson distribution and Wigner surmise are related concepts in random matrix theory. They are particularly prevalent in the field of quantum chaos and studying the energy level spacing statistics of more complex quantum systems. The Wigner-Dyson distribution describes the probability distribution of spacings between adjacent eigenvalues in large random matrices. It can be applied to various different types of large random matrices, grouped together into different ensembles based on their symmetries. For this project, however, we utilized the Wigner surmise, which is an approximation of the Wigner-Dyson distribution. It states that for a 2x2 complex Hermitian random matrix, the distribution of spacings between nearest neighbor eigenvalues is given by this equation at the bottom of the slide here. Now, it has been shown that the Wigner surmise is an excellent approximation both qualitatively and quantitatively to the Wigner-Dyson distribution. So essentially, if our Hamiltonian is chaotic, we expect it to follow this distribution here at the bottom of the slide. And that is exactly what we see. So in red here, we have our Wigner surmise, and the yellow bars are our histogram of energy level spacings. And we can see that the fit here is pretty bang on. And this is only for a system size of n equals 7. As we increase our system size, i.e. the number of qubits in our chain, this fit only gets better. And the only reason we haven't done this is just computational limitations. Next up, we have the average gap ratio, which is often used as an adjoining metric to the energy level spacing statistics. The gap ratio, or I, is defined as the minimum value between two adjacent spacings divided by the maximum value between the same two spacings. The average gap ratio is simply the mean of the gap ratios, where k here is the number of eigenvalues of the Hamiltonian. The average gap ratio can be calculated for various different types of large random matrices. Without getting too deep into random matrix theory, for random real symmetric matrices, the average gap ratio is about 0.53, and for random complex Hermitian matrices, it's about 0.60. And again, this is exactly what we see. So up at the top left of this figure that I showed you previously, we see that the average gap ratio is 0.63, And like before, this tends to 0.60 as the system size gets bigger. The third and final diagnostic we use to verify our Hamiltonian is chaotic is the von Neumann entropy. We use it because the entanglement entropy of a state psi between subsystems A and B is given by the von Neumann entropy. It's calculated by taking the negative trace of rho A log rho A, where rho A is the reduced density matrix of subsystem A, and it is found by taking the partial trace of subsystem B on the outer product of psi. The partial trace here is just summing over the density matrix, summing over all the elements of the density matrix that correspond to a state of that subsystem. If you take a look at this diagram at the bottom here, we can see how this applies to our system. We essentially just split it down the middle, and all the qubits on the left-hand side of this split here are our subsystem A, and all the qubits on the right are our subsystem B. We then calculated the von Neumann entropy of the Hamiltonian eigenstates, EKET, and the reason we did this is because in somewhat simplistic terms, we expect a high eigenstate entanglement entropy for a chaotic Hamiltonian and a low eigenstate entanglement entropy for a non-chaotic Hamiltonian at mid to low energies. And again, this is what we see. At mid to low energies, we see that there are no states. They are all part of this higher entropy band, reinforcing that our Hamiltonian is in fact chaotic. It's at this point that I'd like to remind you of the initial goal of our project, which was to get perfect quantum state transfer through a chaotic Hamiltonian. And at this point, it's not looking too good. So we introduced the Shiraishi-Mori method into our model. The Shiraishi-Mori method is a way of embedding some desired states, psi, as eigenstates of a many-body Hamiltonian. The explicit form of the Hamiltonian is shown here, where these P's are called local projectors, and we need to be very careful when defining these local projectors, as they define the set target states S, such that when a projector operates on one of these states, it annihilates with the state, embedding it at zero energy. This results in a Hamiltonian that annihilates all of these states in S when it acts upon it, meaning it no longer sees this H term, which will be our random or chaotic component. The goal of incorporating this method was to implement perfect state transfer in a subspace S that is protected from chaos. Unfortunately, we couldn't think of any way to do this in our two-level or qubit system, so we expanded our system to 3 levels, i.e. qubits, which Beth has talked on previously. The idea being that perfect state transfer occurs within our qubit space, i.e. our space spanned by the 0 and 1 states, and so this 2 state actually has no role in perfect quantum state transfer whatsoever. Once we did that, we amended our initial Hamiltonian to contain Shiraishi-Mori Hamiltonian, which again is shown here. The only difference from before being these projectors either side of our random chaotic term. The explicit form of the projectors is shown here, and Luke is going to justify why we chose this specific form of the projectors. I just wanted to talk about some of the rather profound results we got from making this slight alteration to our Hamiltonian. So, firstly, we can see that the Hamiltonian is still chaotic. The energy level spacing statistics still follow this Wigner-Sternmeiss distribution I talked about previously, and the average gap ratio is still about 0.60. Again, tending to 0.60 as the system size increases. Crucially though, we still see perfect quantum state transfer, i.e. the transfer fidelity operator, the expectation value of the transfer fidelity operator goes to 1 periodically. This means that we have achieved our goal. For the first time, we have shown that you can get perfect quantum state transfer through a spin chain using a chaotic Hamiltonian. But what's different now than it were before? So if we take a look at our von Neumann entropy plot, we can see that for our Hamiltonian containing projectors, there are n+1 distinct low entropy states that cannot be seen in our Hamiltonian that doesn't contain projectors. It's believed that these are the eigenstates that facilitate perfect quantum state transfer in our 2-level subspace. Some questions still remain though, such as what are these states, how did they arise, and what makes them distinctly different to all the other states in this high entropy band. I'll pass you over to Luke now to hopefully address some of these questions.
Thanks, Pat. So far, we have discussed the relevance of perfect quantum state transfer to quantum computing. We've introduced our XX Hamiltonian, which is our model Hamiltonian. We've defined our projection operators and our random perturbation, which is so far destroying our perfect quantum state transfer. Does anyone have any questions on any of this setup or the structure of anything we've defined so far? Okay, brilliant. So let's take a closer look at these low entropy states and see what's going on here. Like what we have here, these states which are highlighted in black are distinctly non-thermal. This is absolutely not what you would expect. The probability of getting this out of some random collection of matrices is so vanishing that there must be some extra structure here. And the extra structure has come from these projection operators that we've added. So the first natural thing to say is, are these the states that have been destroyed by our projection operator? So if we compute the expectation value of our projection operator with respect to the same set of eigenstates, we can see that our states, which we call the scar states, have all been annihilated. They all have an expectation value of 0. And these are the very same states that are low entropy in our system and falling down from that thermal band. Here we have 8 states for a 7 qubit system. In general, we observe n+1 states for every Hamiltonian we've studied. So what's happening here? Remind you, the structure of our projection operator is the identity matrix, and then we subtract our ground state and our first excited state, both the 1, 0 and the 0, 1. This essentially protects the 0 excitation and the first excitation subspace, which are fragmented out, as Beth mentioned, from our XX Hamiltonian, and allows all other subspaces to be accessed by our random interaction. Again, so to make this a little more clear, if we define these, this is a little error here. These should be 1s, not 0s. These 1 and 0 density operators. This is how we've extended the definition of our Pauli matrices to a higher level system. We've just defined this Pauli matrix as equivalent to the 0, 0 minus the 0, 1. And we can see that our XX Hamiltonian, even this extended energy level space, still commutes with our Pauli matrix, and so we still have excitation number conservation purely with our XX Hamiltonian, which leads to this Hilbert space fragmentation. But pushing on now, with the addition of our random Hamiltonian, there are more states that are annihilated than just our single excitation states. If anything, that doesn't have a nearest neighbor, or neighboring excitations. For example, this 1, 0, 1 state, there's no neighboring excitation, and because this is only destroyed 1, 0, 1, 0, our projector annihilates this state. So our 2 excitation state here, in a 3-level system, would be destroyed by our projector, but this is not showing up in our scars. What's going on? Well, in general, the only states that are destroyed is anything containing a 2, or that aren't destroyed, that aren't protected, are anything containing a 2, and anything containing a neighboring excitation. And so our fragmentation is actually only contains a single direct sum. We have our scar subspace and our thermal subspace. And if we were just to naively expect that anything without nearest neighbor excitations, we would expect far more scars. Does anyone recognize this sequence? It's Fibonacci sequence, which comes out of nowhere. If you can ask me afterwards, I don't have time to give the proof now. But in general, and if we look at just the entropy of our Hamiltonian without the XX, we see all these scars appear. So how has the introduction of our XX Hamiltonian removed these scars from the space? What's happened is that our multiple excitation spaces for the higher Hilbert space fragmentation of the XX don't necessarily have a basis which contains purely non-nearest neighbor interactions and non-nearest neighbor states. And so even though they might theoretically be realized at some number, in practice they never are, as this is a statistical conjecture. I don't have a full structural analysis of the states to say that this will never happen, but in practice we always observe n+1 states because all of these higher excitation states, the algebra never comes together for these 2 processes to align. And so in general, we have our scar subspace, which is n+1 states, defines the states of the XX Hamiltonian, which are destroyed by our projection operator, and we have our thermal states, which are the ones that see our randomness and continue to be preserved. Now, we're defining these density operators just to see what's happening now. We've looked at the statics and the algebra of our setup. Let's take a look at the dynamics. If we take these just the density of our scar state and our thermal state and any operators and any general state, we can take a look at the expectation value of these operators. If we start off our system in a scar state, this is a single excitation state here. Our first qubit is in the first excited state and everything else is in the 0 state. Well, then our process evolves. That orange line at 1, that's our scar density, and our process evolves purely within this scar subspace for the entirety of the evolution, and the thermal subspace is never accessed. And so this evolves exactly as it would under a pure XX Hamiltonian. And this works for multiple states. We can have mixes of zeros and ones, we can have asymmetric mixes of zeros and ones, but as soon as we introduce something from the second excited state in our thermal space, suddenly our star density is no longer 1, our thermal density is no longer 0, our chaotic interactions are accessed, and our perfect transfer is destroyed. So in order to get perfect state transfer, we need to remain inside this scarce subspace. Now, we're still robust to small perturbations here if you say experimentally had some small expectation value of being in the 2 state. Our transfer fidelity is still pretty well maintained here. You can't even distinguish it, but we get up to about 0.995 as the maximum, the transfer fidelity average over the series. And this doesn't decay over time. This retains because our thermal density, our thermal states and our scarce states are completely distinct. They never evolve from one into another through our unitary dynamics. Now, we can look even closer at our dynamics here. So this is a histogram of the diagonal elements of the density matrices of our states. So essentially what I've labeled here is the probability of a state occupying the excited state of the first qubit, the second qubit, or the third qubit, and all other bars which you might see are other states. But if we have perfect state transfer, we should only see probability along those three states. So top left, we have our amended XX Hamiltonian with this projected randomness, and we see that it evolves identically to our pure XX Hamiltonian, exactly as we want. Our random state evolves randomly, and this red Hamiltonian, I haven't messed up that GIF in the slideshow, that's how it's supposed to be. Because it starts off in the scarce subspace, and the Hamiltonian is solely the projectors, well, it doesn't see any evolution. It doesn't see the randomness, so it's just static. There is no evolution, and it stays in that first state. It's effectively like the Hamiltonian is 0 for that state. So, to conclude, perfect quantum state transfer has for the first time been demonstrated on a non-integral Hamiltonian. We only needed local projection operators to tame this chaos, and the dimension of our scarce subspace, which is required to be created, is quite subtle. It depends both on the method of embedding and on the structure of the underlying Hamiltonian that we're acting on. Our implementation was a bit naive. You know, we took this 2-level system and then just said, oh, let's extend it to 3D. We created these projection operators, which, you know, you could debate on the experimental realizability of these things. But we are optimistic of the extension of this method to more realistic models. And as an invitation, we wrote a lot of Python code to make all these simulations that play around. There's a Python class which I wrote now on GitHub, which is about 1,400 lines long. And if you have a little supercomputer sitting in your back garden and you want to extend this to larger N, I'd love to talk to you about that, because the code's all written. We just need bigger computers to run it on. But we hope that these experiments should stay consistent, and we don't see any reason why they wouldn't at larger system size. And finally, on behalf of the whole group, we're very grateful to DIAS for all of the support in mentorship and in financial support throughout the entire summer. We're very grateful to all of you for coming and listening to us talk here today. And we look forward to working again in the future, possibly, especially to Shane, who's been a brilliant mentor and giving up so much of his time for his busy research schedule. So thank you very much for that. Anyone have any questions?
Oh, I do. Would you please remind us what is the definition of chaos in your case? So you said that there are several various properties, like you can measure how chaotic is the system, right? So can you just remind a little bit?
Oh yeah, so
You can go back to the slide.
So basically, we quantify the chaos by saying that it meets these diagnostics, like these diagnostic tests there at the bottom of the slide, because it has no like universally accepted definition, but there are, you know, it's sort of accepted that if the energy level spacing statistics follow the Wigner-Surmise, then the Hamiltonian is chaotic or random, I suppose, but because there's no universally accepted definition, there's not like there wasn't one thing we could do to verify that it was chaotic.
We weren't really able to talk about this too much, but this is kind of motivated by the eigenstate thermalization hypothesis. which basically says if our Hamiltonians and our operators start to act more and more like they've been generated by an ensemble of random matrices, then all of our properties should thermalize as well. But here we've shown from these properties that from these diagnostics they're acting like random matrices, but we're still retaining some sort of properties through these scars that allow us to see integral behavior.
So if I pick up some like generic Hamiltonian, would it be chaotic or most likely not?
Well, if you pick by generic Hamiltonian, do you mean like a random matrix?
I mean, just out of my head. I mean, like if you consider like all possible like scenarios that you can pick up, like how many, like this chaotic case is really special or it's really generic like that? You can, I mean, there are more chaotic systems than non-chaotic in this case, or?
Yeah,
Can you
definitely.
quantify that?
I think this is a way that you could define taking the thermodynamic limit is as you go to larger system size, these chaotic Hamiltonians become the dominant case. And so this leads to a thermalization.
The integral Hamiltonians, I think, would be very fine-tuned, and there's relatively few examples of those. Like systems that map to free fermions would be integrable, and there's a few other examples like the Heisenberg XXE chain would be integrable. Otherwise, there's not all that many examples of integral models. Most would be chaotic. But maybe a disclaimer is that
Yeah, but there's this interplay between non-integral and chaotic, so maybe not one-to-one.
well, I think we were using the two terms
Yeah.
interchangeably. We were saying that non-integral and chaotic are
So
the same.
previously the same.
Yeah.
Okay.
But just a disclaimer that our SCAR method is relatively kind of fine-tuned as well, because as soon as you deviate from the structure of these projectors, then
Exactly.
like shows start to fail as well. So
Are there such projectors known for the XSM model?
for the what?
XSM model.
I know that for the isotropic XXE model, so with the ZZ terms, XXX model, then the projectors will just be the projectors onto the symmetric subspace of two qubits, because the XXE model is permutationally symmetric with respect to things. But for the non-isotropic version, I don't think so. I'm not aware.
So you achieve a perfect transfer from a non-integral model, but I suspect that really non-integral is actually secretly an integral model. Because you start clear with a non-integral Hamiltonian, then first you put projection, the MS projection, and then also you pick up some subspace of Hilbert space, like scar subspace. I think that projected Hamiltonian on the scar subspace. Have you tried to look at, say, what is the energy level statistic of that one? I suspect that is actually the integral.
Yes, so in that scar subspace, if you diagonalize it along that subspace, it'll act identically to the 0 excitation and the 1 excitation subspace of our XX Hamiltonian. But just thinking statistically, if you have any kind of large system size, the dimension of our scar subspace scales linearly with n, and the dimension of our thermal subspace scales as 3 to the n. So very quickly, our thermal subspace is dominant by any kind of statistical measure. But you definitely can diagonalize and take the eigenstates of that scar subspace, and that specifically will be
mixed with the thermal part, and you won't get perfect transfer. I think nothing. I wouldn't say that it's really achieved from a non-integral model. You really achieve a subspace, integral subspace of a non-integral model. Or you can think the other way. So any integral model people started before when they can do the perfect transfer, you can always embed that into a bigger Hilbert space, which you can add additional terms, which is non-integral. So I think in that sense I think it's interesting to see you can do it this way. I think saying that it's not integral is completely misleading to me.
Just that. So another alternative definition for non-integral systems, but for integral systems, is that they should have a number of local conserved quantities that's extensive in the size of the system. So that's an alternative definition that's widely used. But this model doesn't have any local conserved quantities except for energy. So by that definition as well, this would be a non-integral system.
Oh, because usually when you do projections, it always happen like that, so everything becomes non-local. So I think you did check that like the energy level statistic in the star subspace is
Yes,
it is
absolutely, yeah.
okay.
It's integral.
Okay.
Did you try putting an interaction, adding an additional small perturbation which couples the scarf system to the full system? Because that's
Yes, no, that will completely destroy it.
yeah, this is what I said, which is more or less what you say.
But
That if you embed it without coupling it in there, and it just doesn't see the other system. It's a direct sum of two systems. So how your scarf system is sitting in the bigger system.
Yeah.
It's sitting in a non-local way.
But yes, in a sense, it's just kind of like playing with the definition of chaos. I think that's widely used and kind of maybe,
No, that's very nice.
maybe making the point that, you have to be careful about how you define chaos because you can get phenomena like this happening.
I mean, like, what the closest thing we did to that was this demonstration here, where with the TFO with a very small perturbation. And so, like, a small accessing in the thermal state, but that's not quite the same as what you're saying. You're like weakening the projectors.
It's close, but it's natural to put in an interaction where you have you have a coupling between the two systems, which is non-linear.
So we haven't checked that. I don't. If this is sufficiently weak, will we kind of see a similar thing to this, or?
So I think this is perturbing the initial state. So that part of the initial state is in the thermal subspace and part is in the scarce subspace. You expect the proportions in both substates to be constant over time.
Yeah.
But if you change the Hamiltonian so that it generates, as Denjo was saying, generates an interaction between the scarce subspace and the thermal subspace, then that would be kind of catastrophic for what we're doing.
And in nature, it would be, I suspect it's very difficult to construct a subsystem which has zero interaction with the external world and the rest of the system.
Yeah, that's reasonable. But so, like, there would be some characteristic decay time to that, though. And if we were, for sufficiently small chain, if we were refreshing that, we could still achieve relatively high fidelity transfer.
Yes, absolutely.
If we extended that decay time.
You would hope to do that, yes.
Yeah.
Small question, how does your entropy scale with the system size?
This is another interesting point. So the entropy of our scar subspace, of all of our scar states, is constant. It doesn't scale with n. For the numerical, up to n equals 8 anyway, the structure seems to basically be the same and we get constant entropy. In the thermal subspace, it's linear with the system size. So then that's another demonstration of the fact that we basically have an integral subspace. Dr. Wu was saying. Thank you very much.
Is that your laptop there?
Yeah.
Okay, so our second and last presentation will be by Tomas, who was mentored by Dimitri, and he's going to tell us today about exploring unlinkings of symmetric quivers and Permutohedra.
So thank you very much. Again, my name is Tomas. I come from Galway, and I was doing my project for the last couple of months with Dimitri, who I'd like to thank very much for all the help that he's given me. So, as the title says, and as Yaseman said, exploring unlinkings of symmetric quivers in Permutohedra. So this talk is going to be a little bit different, I think, from the topics that were covered in previous talks. It's my own background is in like pure and applied mathematics in my course. So we don't really focus as much on the physics here. It's more a mathematics project, but the applications are there. Back to it. So anyways, just a little bit of a brief introduction of why we're interested in quivers, or maybe I'll introduce what quivers are to you first. Yeah. Okay, that's better. Yeah. Sorry, there we go. So a quiver, very simply, is just a direct and multi-graph. So if you think of a graph, you think you can have multiple edges between nodes, and they're directed. And well, there's a little bit more of it's a little bit more rigorous up there, or are you just talking about sets and you have arrows between the different points and you have functions that assign sources and tails to them? But that doesn't really matter. What matters is what we're going to be talking about mostly is symmetric quivers. So a symmetric quiver is just a quiver, but for every arrow that goes from A to B, there's an arrow that goes from B to A. So we have every arrow comes in pairs. So whenever I discuss a quiver, I really mean a symmetric quiver. So why are we interested in these objects? So a couple of years ago, a collaborator with Dimitri found that there is this correspondence between knots, topological knots, and quivers, and specifically symmetric quivers. So what this actually suggests is that these quivers can be used to study these knots. What you have the correspondence between is actually representations of symmetric quivers, and their moduli spaces can encode information about the homology groups of these topological knots.
Did you say what symmetric means?
Symmetric means that you have, for every arrow that goes from A to B, there's an arrow that goes from B to A. It's just in the way that you might think it. So you have like the examples here, where you have every arrow comes in pairs. Of course, you have an arrow that points back to itself. Here, it's the same thing, except just to keep the graph a little bit neater, instead of actually putting the arrows, you just draw it as a normal graph. But you can have repeated edges. But this knot quiver correspondence is interesting because it actually suggests that we can use these quivers then to build more robust homology theories for knots and three manifolds. Also, you have the link back to physics, so quantum topology. When you're studying BPS states and their degeneracies in supersymmetric gauge theories, all of these things link back to that study. So actually understanding the structure of these quivers, the structure that ensues from this correspondence with knots, is a very useful tool to actually developing this theory a little bit more. So, yeah.
More than one arrow going from S to T?
Yes, it's a multigraph, so you can have as many arrows as you want.
But when you have two going from A to B, then there's also two going.
Yes, exactly. They always come in pairs. So, and we can encode that. The way we're going to do this in general is we're going to have an adjacency matrix or something that's like an adjacency matrix. So, let's say entry ij is going to be how many arrows there are going from I to j. And because it's symmetric, that matrix is going to be symmetric. So it makes it nice to work with, and they're the only types of quivers that we're going to consider anyways. So I mentioned quiver representations. The reason I'm introducing this is because I'm going to be talking about equivalence of quivers later on. And to understand what the equivalence is, we have to understand how we represent them and how we encode information about our quivers. So a representation of a quiver is just a collection of vector spaces and linear maps between them. So to each node in our quiver, we're going to assign a vector space, and to each arrow, we're going to assign a linear map. Yeah?
Sorry, you said you can connect it back to itself.
It's just an arrow it's like a loop.
So then, does that have another, you said it goes symmetric, so that's it.
They're on the diagonal, so it doesn't make a difference. Yeah. Anyways, yeah, so we have a representation of our quiver. And to be clear, we're not just talking about any representations. The representations that we're interested in are specifically finite dimensional vector spaces over finite fields. So, f sub q, where q is some power of a prime. And with that, we introduce actually an important quantity. I haven't included it on the board for some reason, but it's called the dimension vector. So it's just, if you have, let's say, m nodes in your quiver, your dimension vector is just going to be if we number them, label them numbers, our dimension vector tells us what dimension each vector space is over its base field in our given representation. And that actually shows up in this quiver generating series, because now we want to be able to represent or store the information about the possible representations or properties of those representations that we have for our quiver. So here it is, PQ, and then we have these formal symbols, x1 to xn, which we call our generating variables or generating parameters, and we've got this Q symbol as well. And we just define this formal power series, and these are the coefficients here. And it looks a bit scary. It's actually interesting because this number here is plus or minus the size of what we call representation space. So it kind of it encodes information about how many possible assignments of linear spaces there are to our quiver, or not linear maps, I mean, to the arrows. And then what we have here is just the actual variables or formal symbols in our power series. So it's just a generating function. Interestingly here, this thing might look a bit strange, is a Q puckhammer symbol. So a puckhammer symbol is just, it arises in combinatorics and special functions, things like that. It's just a rising factorial. If you think where you're taking a n factorial, you go down, and for a rising factorial, you go up. And a Q puckhammer symbol is a Q analog of that. It's just another tool from combinatorics. And this type of symbol arises in like Q hypergeometric series, things like that. But for here, it just works for what we want. So we have generating series, we have quivers. Now we want to be able to relate these quivers to each other. So how do we do that? Through the generating series.
Is series converges?
No, it's just a formal power series. It's just a formal expression. It doesn't even, convergence doesn't really come into account because we're interested in what the coefficients encode rather than what the series actually is.
But you also said it's just a finite series.
No, it's infinite. We're summing, sorry, I should have said we're summing over all possible dimension vectors. So, so we're really what we're doing is we're encoding the information about any possible representation of our space, or in a finite representation with the finite dimensional vector spaces. But yeah, so we say that two quivers are equivalent, so we have two quivers, Q and Q prime. We'll assume without loss of general a Q prime has more nodes than Q, just because it allows us to make our change of variables. And then we say that they're equivalent if we have a look at their two quiver quiver generating series, and we say they're equivalent if they're equal up to some monomial change of variables. And that's what we have here. So for every xi here, so x prime I is ranging from 1 to n, and you just do a change of variables. And if you have that change of variables and that exists, then we say the two quivers are equivalent. This might seem a bit strange for why we're defining this. Once again, it comes back to the not quiver correspondence. The way that the quivers, I won't get it too much into it, but the way that the quivers correspond to the knots is by looking at another generating series that's associated to the knots. So what we have, yes, sorry?
So what are those exponents there?
So these size are just some powers that you're raising everything to. This is a monomial term. It's only a single term, but we are free to choose the different powers of the terms that we want, just to make these two series Sorry?
They're arbitrary integers.
Yeah, they're arbitrary integers. Or they're not arbitrary because we choose them, we make a special choice such that the series are equal. But like what they are doesn't matter. As long as it works, it works. But what I was saying is when we're going back to the knots, so knots, we can a certain way we can represent a knot, or the characteristics that we're interested with the quivers, is through the colored Humphrey PT superpolynomials. We can make another formal series of those, another formal power series. I won't go through it. If you want to ask me afterwards, I can say a little bit about it. But the way that we relate the knots to the quivers is through a correspondence between the quiver generating series and this generating function of superpolynomials. So what we're saying is, with this correspondence, we can say that these quivers are capable of holding the same information about the knot, because we can relate them in this way, in the same way as they're related back to the knots. So it gets a little bit confusing, but that's why we're introducing it. And then we have, this is just an example of two different quivers that are related to each other, or that are equivalent. It looks a bit arbitrary. You might think, well, okay, this one quiver is bigger than the other. That has 4 nodes. That one has 6. how do we know that they're equivalent? So you could go through, like, the generating series is defined in terms of its adjacency matrix. Like it's just a function of the adjacency matrix. So you could just compute the adjacency matrices, compute the power series, and show that they're the same. Or what we did here is we actually find that this quiver here is constructed from this one using a special operation, which we call unlinking. So I'm going to give you this unlinking operation is kind of central to the project, or to the work that myself and Dimitri were doing. What we do is, given a quiver, this is just a very high level overview. You select a pair of nodes which are connected. You remove a pair of arrows between them. That's the unlinking part. But then you do extra operations in introducing a new node to the quiver and connecting that back to your original quiver in a specific way that preserves the power series up to a change of variables. It's actually just one little change of variables that you have to make, and those quivers turn out to be equivalent. This is an interesting operation because if you look at the operation, if you naively take all possible unlinkings, so you're going to have those alphabeted symbols which you can unlink with each other. If you introduce an identity element, if you close it under composition, you get a monoidal structure. And then a question arises like, okay, what type of structure do we get when we look at equalities within the structure? So we're going to call equality between two sequences of unlinkings. So we apply one unlinking and compose them with each other over and over again. What type of structure ensues when we do that? It turns out it's very restrictive, and we only get what we call three basic relations. And maybe I should say as well, we say that two unlinkings are related. If we apply, given any quiver, we apply these sequences of unlinkings, we get back to the same quiver at the end. Not the same quiver as in the one we start with, but you apply the unlinkings and you get back to a quiver which is equal, I suppose, up to graph isomorphism. But yeah, so we get three very specific types of unlinkings. And it's this. Not every element in our set is going to commute with each other. So if I encode it like maybe a little bit like a commutative diagram, let's say we're unlinking nodes I and J, and we're unlinking nodes K and L. We want to see, well, what can we do so we can get back to the same quiver? These actually commute with each other. So in our monoid of unlinking operations, we have that if there is no repeated index in our unlinkings, we can commute them. So that's the first type of relation that we have. The second type is if we do have a repeated index. So obviously if the two indices are the same, the unlinking is the same, we have identity. But if we have a repeated index, so let's say ij and jk, we get two different types of unlinkings that we can perform. They're related to each other, but we'll call this one a square, we'll call this one a hexagon, because this commutative diagram, or like-looking thing, looks like a hexagon. So we get jk, ij, ijk, and jk. So we need to remember that with every unlinking that we perform, we introduce a new node. So the new node will be named after the unlinking that created it, and we get this hexagon relation. We can also do the same thing, except we can swap these. So we can do ij, ijk, followed by jk, and that's the second type of hexagon relation. But in general, this is the one that we're interested in the project for what we're doing later on. Another note of interest is we call these unlinkings up here associativity unlinkings, and the interesting thing about them is these are distinct unlinkings. ij is created here. ij is not in this path. Oh, it is in this path here, but we're doing a different operation. We're unlinking jk with I, and here we're unlinking ij with k. However, when we perform this operation, we get back to a quiver which is equal up to isomorphism. So it means that we can actually identify these nodes with each other. So when we're performing our unlinking operations, later on we're going to be doing more complicated unlinkings. But we need to keep track of like how these different nodes are identified within our quivers. So those are the two different types of basic relations. And how do we know that's true? Well, in a paper that Dimitri and his collaborators wrote, they introduced a theorem called the completeness theorem, which says if you have any relation within your monoidal structure, they can always be related to each other through some finite sequence of square and hexagon relations. So these are the most basic building blocks of what we're going to be working with throughout our project. So now having looked at unlinking, the next tool that we will need is the idea of a connector. So given any two paths, so I'm going to call a sequence of unlinkings a path, and it'll kind of make sense later on because of the diagram that we produce. If I give you just any two arbitrary paths, is it possible to do another sequence of unlinking such that we get back to an original relation like this? We get back to the original code. And the answer is yes. We call such a thing an NN connector. So we have a sequence of length n, or path, and a path of length n. Then an NN connector is just going to be two more sequences, so we call them UI prime, J prime, and UK prime, L prime, such that when you compose them with your original two paths, you get a relation within your structure. Here, we already have some examples of connectors. If we look here, if we start with IJ and KL, well, JK, KL and IJ, that's a 1-1 connector. Same thing we could do here. We could start with IJ, JK, compute those two connectors. There's two possible connectors actually we have here, but we still have a 1-1 connector. Or if we start with these two, you get a 2-1 connector. What this actually illustrates, and especially what's talking about here with the connector theorem, is Dimitri introduces an algorithm that we'll use later on in the project called the connector algorithm. And maybe I can just show you just quickly how, maybe give you a taste of how it works. If we started with something like this, so instead of using IJK, we'll just use numbers as our alphabet symbols. So we might start with 1, 2, 3, 4, 5. And the taste of how this connector algorithm is going to work is we go layer by layer. So we start with the first layer, we got 1, 2, 2, 3, repeated index. We're going to apply a hexagon. So it's going to be 2, 3, 1, 2, 3, 1, 2, and 1, 2, 3. The reason I'm doing this type of hexagon is because I have it on my page and I know it works. So we're going to do the next layer, cut it along here. What's to be connected? Well, these two are to be connected. This is separate. You don't worry about that. 2, 3, 4, 5. And finally, last layer, we have two more to connect. So this is going to be 1, 2, 3. And this is going to be 4, 5. So what we have here is that starting with these two paths, we've been able to connect them. This idea of a connector is something that's very important because what we're going to do is we're going to move on to structures, which we'll call Permutohedra of Quivers. And what we're going to be interested in doing is actually unlinking them using these connectors such that we can break them down or build them up to something that encapsulates the whole structure in a single quiver. So just a quick note on the connector theorem. All it's saying is if we have two paths and we want to connect them, the connector exists. And that's proved using the connector algorithm. It pretty much just jumps straight out of that. So the final tool that we're going to need is Permutohedra. So a Permutohedron is just a combinatorial structure. If associated to some symmetric group. So if you have sim n, there's n factorial permutations. Each permutation is assigned to a node of a graph, and those nodes are connected if those permutations differ by transposition of adjacent elements in this image. So you're going to get, that's pi 4. That's what, if you think of sim 4, has 24 nodes, that's what pi 4 looks like. There's simpler examples. You have pi 2, which you can label the nodes, let's say it's going to be 1, 2. So that's the identity element, corresponds to the identity permutation, and 2, 1. And those are connected because they differ by a transposition of adjacent elements. There's only 2 elements. Also, you have sim 3. I'll just draw this up here because I'm going to use it a little bit later. And that's a hexagon. 6 elements. Bad hexagon, but it's a hexagon. And you're going to note there's 3 distinct transpositions, or like transpositions in sim 3. So you can actually, these opposite edges correspond to the same transposition of elements. But you can label these like this be 1, 2, 3, this be 2, 1, 3, and this would be something else, and this would be something else. So you get that's a permutahedron. It's just a way of representing the symmetric group in this kind of geometric way. And what we're interested in is actually constructing permutahedra of quivers. So it's going to be a bit confusing, but what we're doing is we're constructing more graphs, but each node on the graph actually corresponds to a quiver rather than the graphs that we're looking at being a quiver. So what we do to do that is we start with a seed, which we'll call.
What's the dimension of your permutahedra? Oh, with n. What's the dimension of the symmetric?
Is it n-1 for, do you know, Dimitri?
Sorry for what?
If, like, just the dimension of, if you're drawing it as just a geometric object, so for pi n, it'll have dimension n-1. But yeah, so constructing, what we're going to do is we're going to start with a seed that's just like a quiver, and we're going to perform a sequence of linking operations in a specific way, which is defined by the permutations in set n. So you need to make sure your quiver has enough nodes in it first to compute all these unlinking operations. So we're going to label them iota j1 to jn. So we need n plus 1 elements, or n plus 1 nodes. And then just perform a sequence of unlinkings by just permuting the different, going over all permutations of the unlinking sequence that we can have for, n elements. And that gives us, we call then that set of quivers. So we'll just define them by q sub sigma or q sub the image of the permutation or whatever you want to call it. And that will be what we call our pi n, which is our permutahedron of degree n. And that's the important thing that we're looking at. So maybe a question that arises is, why do we care? Like, why do we care about these permutahedra? Why am I introducing them? Well, it comes back to the knot quiver correspondence again. When we're looking at the knots, we don't have it with the knot quiver correspondence. It's not the case that we have a bijective correspondence between the knots and the quivers. Many quivers are capable of holding the same information about the knots in question. But one question that might arise is, well, can we apply or can we put some structure on these quivers? And the answer is yes. In the simplest cases, we can arrange some of these quivers to form a permutahedron. More generally, it won't be a permutahedron, but what it might be is what we call a permutahedron graph, which is, if you just imagine taking many permutahedra and gluing them together, and that constructs a new type of graph that we don't concentrate on in this project. We just look at permutahedra, and that's what's important to us. But that's the type of structure that arises from this knot quiver correspondence. So if we are using quivers to study our knots, then possibly what we would like to do is, how do we choose a good quiver? Like, there's a lot to choose from. Like, here, there's 24 quivers in this thing. Which one do you choose? Which one makes your work easiest? Or how do you remove the redundancy? That's where the idea of universal quivers comes in. So everything we've done so far, we now want to apply the idea of connectors with our permutahedra and see, can we actually perform unlinking operations on each of the nodes of our permutahedron such that we connect them back all to a single equivalent quiver, which we'll call a universal quiver. And so that gives us maybe an idea of maybe a unique element that we could work with to study set knots. So that raises the question, can we do that? Yes, the connector algorithm can be used just to show that such universal quivers exist. And if I show you here, this is an example that was presented in Dimitri's paper, and this is where I kind of work off. It doesn't have any labels in this graph. Here, the labels are too small to see. But every arrow here, so every node corresponds to a quiver. You can see here it's a hexagon to start with. So these outside edges correspond with the permutahedron element quivers, and everything inside are like intermittent quivers until we get to the quiver in the middle, which is the universal quiver, after so many unlinkings. So here we have 1, 2, 3, 4, 5 unlinkings, and that brings us to the universal quiver. This is just a different view of the same diagram, except these dotted elements at the bottom represent the underlying construction of our permutahedron. So we have a seed down here, and we have the different paths that are traversed to get to the quivers of our permutahedron. When we have a permutahedron, those unlinkings or this seed quiver isn't there explicitly, but the actual structure of the Permutohedron remembers the structure, because by definition that's how we construct a Permutohedron of quivers. So when we want to perform these different unlinking operations, we are severely constrained by what operations we can perform in the first place, just due to the underlying structure. If we want the first move to unlink anything is determined by what came before it, all we can ever do, because of the completeness theorem that I mentioned, is apply square and hexagon relations. So this is a nice example of the universal quiver for pi 3. But can we do better? Is that unique? And the answer is no, it is not unique. And one of the first things I did was to go and find other examples of universal quivers for pi 3. These are some of my handwritten constructions. They get very involved. These are quite small examples. They're examples which are larger. And one might ask, oh, how do you know that these universal quivers are distinct from the other, from the quiver that was shown in the first place? Well, it's very simple. I use a different number of steps. Like this one here uses 1, 2, 3, 4, 5, 6 steps. This one I think uses 9. So there are a different number of nodes in those universal quivers to start with. There's no way they can be isomorphic. So they're not the same. So the universal quivers are not distinct, or not unique, I mean. But then the second question that arises is, well, what's the best we can do? Can we find a minimal universal quiver with a minimal number of steps? It turns out we think that 5, if I go back to this example, is the best we can do. And I have a bit of an argument that can go along with that. You can think of unlinking pi 3, so we imagine this to be pi 3, and you can think taking it step by step, where I'm not going to do it explicitly, but by taking pairs of elements, so let's say we take a pair of elements which are separated by one transposition of adjacent unlinkings. How can we unlink that? Well, you can do that in one way, because as you see here, there's underlying structure. So that informs you what you have to do. So in each case, you actually have to close a hexagon or close a square, and you introduce a specific type of unlinking. That actually, for the whole graph, introduces 3 different associativity unlinkings, and they're all distinct. And our strategy is, if we want to get to a universal quiver, along any path, we always have to, it doesn't matter what order we introduce them in, but we always have to introduce the same associativity unlinkings. Because if we want our last quiver to be equal, well, it has to have all the same nodes, and every unlinking introduces a special type of node. So in the first step, even, if we are informed that we have to link adjacent quivers, so that introduces 3 specific types of nodes. So this side and this side, we unlink these, and we unlink these. The associativity unlinkings, or the nodes, are going to be equivalent to each other. So opposite sides always introduce the same type of node. Then we do the same thing. We look at things separated by 2. It turns out you can do that using that, in that case, for that step, everything commutes with each other nicely. So we don't introduce any new types of nodes. But if you want to have a look, what's the maximum separation in pi 3? So 3 transpositions of adjacent unlinkings. And in that case, you find that these quivers, when you connect them, actually there was 2 distinct ways to connect them. You can see it in the diagram. I can go through it in a little bit more detail if you want me to. I won't do it right now. But what you do find is that 2 more distinct, classes of associativity unlinkings are introduced. So that's 5 different classes of associativity unlinkings. And you know that in any path, all of those associativity unlinkings have to be introduced in it for the last quiver to be equivalent, or for the universal quiver to exist. We have an example here where it takes 5 unlinkings to get there. That means, well, necessarily, this is the minimal number of steps that we need, because in any construction, you need to introduce at least 3. So that's the argument to show, that's some type of justification for why this one is the best case. So the next thing we wanted to consider is pi 4. We've looked at pi 3, we've considered the structure that comes from unlinking it to universal quiver. Can we use the same type of reasoning to find universal quivers for pi 4, and even reason for find minimal universal quivers for pi 4? We know the minimal quivers exist. It's very simply because universal quivers exist. Take the set of all the universal quivers, look at how long each of the paths are. Well ordering is just going to tell you that there's a least element to that set. There's going to be a least universal quiver.
just there could be many.
We never claim that they're unique. That's not something we've properly checked. But what we wanted to try and extend some of the reasoning that we used for pi 3 to pi 4. Turns out moving from pi 3 to pi 4 is a lot more difficult than we might have expected at the start. Hand calculations are not quite as nice. And Dimitri saw some of the calculations that I did, and they get messy very quickly. So keeping, like with the same type of strategies we're trying for pi 3, you're keeping track of all the associativity unlinkings that you're introducing. You're keeping track of the relations between them. You're keeping track of what type of relations you're using the whole time. It gets very much out of hand. And while we had nice planar graphs for pi 3, when you move to pi 4, it's not planar anymore, so writing it on a piece of paper is quite horrible. So what could we do? So I mentioned the connector algorithm earlier. You see that when you do it up on a board or on a piece of paper, it's quite a nice construction. The diagram itself holds the information that you want to about how the different paths are related to each other. Implementing that on a computer, problems arise. You have to keep cross-referencing different paths and all these things. It turns out that using graphs is not a very nice way to do it. So there's a symbolic approach you can use, as is described in Dimitri's paper, and that's what we try to do. So using Julia and also some functions that were predefined in Mathematica, we implemented the connector algorithm to work on just to compute connectors, and then we can throw the output of that into Mathematica, and what it'll be able to do is reverse engineer the one path you've discovered to create the whole linking diagram as we have here. So we did that, but work for pi 3. You're able to just find just any example of a path. So let's say we chose this one here, go up to the middle here, and we plug that back into the Mathematica function, and it spits out the entire diagram. And sometimes it spits out a little bit more because in the initial stages, when you're constructing pi 3, there's some links that you don't make, because when in Mathematica it goes all the way back to the seed quiver. So what you do then is you truncate it at the level of pi 3 in this case, and you get this diagram. But so how we're going to use that anyways to construct pi 4. So here's a simple example that we looked at just as a strategy to try and compute pi 4. This is just a simple thing where we start with 2 unlinkings. Let's say 1, 2, 2, 3. And we can compute a connector for them, as we have there. And then we introduce a new unlinking. And then using the output of the previous step, we compute a connector again. We keep iterating that process as we move. So 1 iteration, hexagon. 2 iterations, we get this. Then we keep going, and like every time we see the same structures arising. Like it's kind of like it looks like a fractal structure in a sense, but it's not surprising because, of course, when you add a new node to the end of it, you want to connect that to all the rest of them. You're going to have the same structure within it, and connecting the substructure, I suppose, connecting the sub collection of unlinkings that you start with. So our idea was, if I go back to pi 4. Can we traverse a path through pi 4 in the same way, where we iteratively compute connectors between those quivers, take the output, put it back into our function, and keep computing those connectors until we've used enough nodes such that it encapsulates the whole structure of the Permutohedra. It turns out just trying to brute force it, just trying to use all the nodes and go around, doesn't work because there's just there's too many variables to keep track of, too many paths, and you're cross-referencing them. You have to not only do you store them, you have to store the relations between them, and just the computer kind of gets overwhelmed, or my laptop did at least. So trying to find a good path or a smart selection that minimizes how much data is stored was ideal. We got this far, so go back to. So this is the sequence of unlinkings that we considered. So we started at Q1, 2, 3, 4. So we're just thinking of the nodes again on that the previous diagram. Every node corresponds to a quiver, and every quiver is what you call constructed in the way that we described for Permutohedra. So we have Q1, 2, 3, 4, and we did a linking with Q2, 3, 1, 4. That's this. Very nice and simple, doesn't take much time. Then we add in this node, and we take one of the connectors there, and we re-put it into our function with a new node. We get such a structure. Again, we see this structure rising here. Then we take that, and we then add it to this. And suddenly things start getting a little bit bigger, but it doesn't seem out of hand. It seems like it's still a reasonable looking object that we can compute. And again, we see that structure just appearing just down here. But we notice that by adding just one more node, we need a lot more unlinkings to introduce all the associativity unlinkings that we want for each path. And then to finally move into the last path. Adding one more unlinking to the list suddenly makes things explode a bit. At this stage, my computer was struggling to compute what we needed to compute, and we did get an answer. Yeah, there we go. This structure encapsulates about half of pi4. So we get, I think, 14 nodes, so a little bit more than half of pi4, and we unlink all of them to a universal quiver for those nodes. Adding one more node, I ran it overnight, I ran it for hours, I made changes to the code, I tried to optimize it. I couldn't work in the time I had to actually improve it to get something encapsulating the whole diagram. So this is the start we got for pi4. It turns out that looking at the structure that we got for pi3 and even for pi2 here, which is the simplest case, you can just use one unlinking to get to a universal quiver. Here we can use 5 for 4. There so far we have about, I think, 18 unlinkings in a given path. Once you get to 20 unlinkings in the computer, it doesn't want to work anymore. But what we see is maybe looking at smaller structures and trying to infer patterns from small examples is a nice idea, but when you actually move up, it turns out keeping track of all the unlinkings is quite difficult, and it isn't as simple a structure as we were looking for. So I suppose going forward, we're definitely close to an answer. The code that I've written can be optimized. It's not perfect by any sense of imagination. There are bugs in it, and it can certainly, I can store information in a better way, cross-reference it in a better way. And I think we can actually, we can get to a connector, or a universal quiver for pi4. However, at the moment, this is all we have, but it's still informative in the sense that maybe the structure that we were looking at in the first place isn't actually as simple as we might have expected. So I think I've spoken for a while now, so I don't want to keep you any longer. But thank you very much for listening to me. I would also like to thank Dimitri again for all the help that he's given me over the last couple of weeks. Yaseman and Shane, you both did. Thank you very much for organising all this, and Denjo as well for having us in Dias. So that's it for me. Thank you very much for listening. And any questions? Yeah?
I was just wondering, like, at a practical level, what was going wrong when you tried to brute force this on the computer? Was it that you ran out of RAM, or was it just taking too long?
So it's down to how when you with every level you construct a load of new paths, and with those paths you also have to remember how they're related to each other. So the idea is, if you are smart in which connector you take and which next unlinking you use, you can reduce how many things the program has to store. In the sense of, like, if you had some weird path here and then the path here, and they're connected to each other in some way, and you want to connect that to a new node. Like, let's say we want to connect it to this. So we have this to begin with. This is the output of the connector algorithm in one thing. And here we have another path which we want to connect back to this. You have two choices for from the output of your algorithm. You have this path here, and you have this path here, just kind of as you see on the board. This path here more closely resembles this one here, because in the initial unlinkings, they don't, the way they differ are less, if you get me. And this one is further away from it, because you make a number of initial unlinkings, which brings it further away from that path. So if we try and do the algorithm with this path here, what you have to do is not only do you have to do the connector for all of these, which for this and this, but you also have to compute everything in the interim, if you get me. So by selecting this path here, you're actually having to store less data, you're having to store fewer the relations, and the computations are reduced. We try to chunk it up, because if you just try to do everything at once, it just gets overwhelmed. So the idea was, there's definitely redundant data in the program that has been written. So getting rid of that redundancy would definitely speed it up a lot. But by selecting your paths properly, it kind of reduces how much redundant data that you produce in interim.
So it's when we run out of water quickly.
Yeah.
I missed what in the end is the advantage of finding this universal? Because it's not universal.
It's
an universal.
And universal quiver, yes, exactly. It's not unique.
But it doesn't, since it's not unique. If somebody else comes up with a universal quiver which is not the same.
I suppose, well, from my perspective, like, this was just a problem to look at. From a mathematical perspective, it was just kind of, can I do this? And that's maybe a cop-out answer. Otherwise, I know what Dimitri was mentioning is when you're studying the knots, you do want to, there is redundancy in the fact that there are many different quivers to choose from. The fact that universal quiver in some way encapsulates all the information that's stored, or that is capable of being stored in the Permutohedral, in that Permutohedron corresponding to the knots. So
Even that it's not unique is the real problem. It hasn't solved, I don't see what problem it could have solved.
Yes, maybe I can comment.
Yeah.
So in fact, it was a little bit disappointing that these are non-unique, but so like the bigger plan was like to study what is the structure of such universal quivers. I think what Tomas achieved, like making this very nice program, and hope to somehow to investigate the structure of these bigger quivers that we obtained from such operation. So this is like one of the questions.
So you're thinking that universal quivers may be equivalent if you understand up to some transformation which maps one into the other.
Yeah. So the hope that they form some like nice structures, and even in this case of pi-n, so the conjecture is that there is a unique minimal such quiver, so that you cannot obtain another one, but this is a conjecture. So this is like 5-step picture that must.
Yeah, no. If you have a unique thing, I can see the point.
We didn't construct like other cases, but so far we cannot also prove that there are.
Why is it believed that there's a unique one for pi-n? Or unique minimal one for pi-n?
So there should be some sort of induction argument, but yeah, we don't have like yet. But in this lower cases like pi2, pi3, yeah, this is true, just by experiment.
I know you focus on the mathematical aspects of these covers. Can you say a little bit of that? Physical applications?
Yeah, I can. I was briefed on this a little bit by Dimitri, but there's a couple of ways. Obviously, what I said at the start. So even from a maths approach, you're looking at discovering. You're looking at building more robust theories, homology theories for knots and three manifolds. But the knots and three manifolds can be used in physics as well. The idea is if you have a symmetric quiver, you can construct from that. You can construct. What do you call it? You can construct a given quantum field theory whose gauge content or field content is encapsulated by that quiver. So the quiver generating series that we introduced earlier, that series itself will be a partition function for that field theory. And so actually it encodes information about the BPA states, or it'll actually give you a BPS spectrum. So it'll encode information about the BPS degeneracies of that field theory. That information itself is encoded in the form of these Donaldson-Thomas invariants, which are invariant for our quiver. So what we can do with their generating series is actually we can perform a couple of transformations on it. I think it's using a platistic exponential function, and you can construct a product form of the series from that. And within that, you'll find a generating series for these Donaldson-Thomas invariants. And the nice thing about them is I can't go into why this is true, but the interesting fact is for symmetric quivers, you actually find that these Donaldson-Thomas numbers are integers, which seems strange to me anyways, because things don't just normally show up like that. But those numbers themselves encode information about these degeneracies. So that's the direct link to maybe to theoretical physics.
So what is happening to the adjacency matrix when you're mapping between these curves?
Okay, so that's actually so this paper here gives a detailed explanation of exactly what you're doing, but it's all defined in terms of the adjacency matrix. You take an input of a matrix, your input matrix, and what you're going to do is you're going to do a transformation on it where you introduce a new row and a new column, which corresponds to the new node that you produce. Obviously, you're removing a pair of arrows, so you're going to remove those from the correct positions. And then in the new row and the new column, there's a pattern of numbers that you put into it, depending on which nodes you're unlinking. So it's just you specifically add different things together and subtract one maybe, and just so that you get the proper thing. I think it's this. I'm not sure. Maybe this is a bad idea, but we'll probably get it wrong. I think the idea is that you have everything is C11, so you go over to maybe it'll be Cij, and you're going to Cij in this one. We're going to have Cij in this one. So we're linking I and J, and then we have, so that's our original matrix. So we remove the arrows between those, and then what we're going to do in the new rows, we're going to add. That's going to be like, is it C? There's going to be a thing where you're going to add C1I plus C1J. And you're going to go all the way down, except for in these rows where it's going to be C1I or C ij or something. There's going to be a way of adding things together here, and then you minus one. So it's going to be the same as this minus one, and then down at the very bottom there's another little combination of previous entries from this matrix that you use to transform it.
So why don't you use that to try and find the universal?
Oh, that is used. So in the Mathematica code, and that was provided by Dimitri. Like this is the basis of how we actually construct the universal quivers. We can reverse engineer this algorithm to work our way back down the path and then construct the whole diagram.
This doesn't look like it's so memory intensive.
No, that's not though. It's what we were doing here is we're purely symbolically trying to compute the connectors, not by actually keeping track of quivers, but keeping track of sequences of symbols, pretty much. And with every step we introduce a new symbol. And so we're storing all the paths, and then I was using this data structure called a disjoint set forest, where it's used in graph connection, like when you're checking connection in graphs. I was kind of storing all the paths as a graph, and then you just keep rechecking, are the paths that we need connected with each other? And that it keeps doing that until it eventually finds a path and then terminates and spews those out. So like actually doing that stuff is not that intensive. Like Mathematica isn't that fast. Julia is a lot faster, but it's just the way I implemented it is quite naive. Programming certainly isn't my strong point, so it kind of 100% be improved to remove the redundancy as well. There's a lot of information there that's stored that doesn't need to be stored, and I think it's just the fact that you're getting these really long lists of things that you need to keep checking. Do we have inclusion? And then after, do we have inclusion? Are these things contained in the same subset? And that's done over and over and over again. So that's the intensive part. I don't think it's a mix between how much RAM I had on my computer, but also just there were a lot of operations that were repeated over and over again, and the way the information was related to each other probably wasn't optimal for what I was trying to do.
You should talk to the causal set people.
Oh yeah, Dimitri said I should have mentioned that actually. these diagrams, don't ask me how, but these diagrams that we created are in some way able to represent causal sets. I think you
They
said.
have a posted structure.
Oh, certainly, yeah. Yeah. So I was told to say that to boost interest. But yeah. There we go. Any more questions? Okay, thank you very much.